Another target is the bacterial synthesis of their genetic material, DNA or RNA, and there are some groups of drugs which act in this way. First of all, by interfering with the metabolism of folate or folic acid, and secondly by directly inhibiting the synthesis of DNA. Now basically all of these drugs have got the same endpoint. They get in the way of the ability of the bacteria to make new DNA and therefore to copy their DNA in order to undergo cell division and replicate. So the sulfonamides and trimethoprim, and we'll look at these together, are drugs that prevent DNA synthesis and RNA synthesis by inhibiting folate metabolism. And the quinolones are drugs which prevent DNA synthesis directly. Okay, so let's have a look at those drugs. The sulfonamides. The sulfonamides, you can tell, all have the sulfur in their names. Sometimes, depending on which kind of text you're looking at, it may be sulf as in pH in the British spelling, or it may be SULF, but it's the same thing. So if it's got sulfur in, it's a sulfonamide. And trimethoprim is an agent on its own, but we're putting them together because they essentially have the same effect, or at least they affect different points on the same pathway, so we're going to lump them together. And they are actually lumped together in some drug preparations. If you've ever seen or had a drug known as cotrimoxazole, it is in fact trimethoprim, hence the tri, and sulfamethoxazole, hence the moxazole, combined together. And here's how they work. This is basically a very brief and simplified metabolic pathway involving folic acid and its metabolites, and how they're involved in the production of certain nucleotides which are required for RNA and DNA synthesis. And the whole thing starts with PAB or para-aminobenzoic acid, going through folic acid, dihydrofolic, tetrahydrofolic, and then you actually synthesize your nucleotides. So what happens is the sulfonamides as a group, all of these sulfur drugs, inhibit the conversion of para-aminobenzoic acid to folic acid. So that's how they inhibit this production of the nucleotides which then are going to make up RNA and DNA. And trimethoprim acts on that same pathway, as I said, but a little bit lower down. You don't need to learn that, I'm just using it for illustrative purposes. So I don't need you to know exactly where on the pathway trimethoprim or the sulfonamides act. But you can see that if you combine the both of them, you'd have a double whammy for inhibiting this pathway. So hence they are bacteriostatic, they stop the division of the bacteria. Their use is now very limited because, one, they've always had a fair few adverse effects, but they're also now getting a lot of resistant bacteria that aren't susceptible to these drugs anyway, so no point in using them at all. They are still used for pneumococci and meningococci. That would be quite serious infections, septicemia, and they can be used for gram-negative UTIs, urinary tract infections, possibly. They also have some potential for causing allergy because of the sulfur component of the drug. And if a person is allergic to a sulfonamide, then they are likely to be allergic, because it's usually the sulfur that they're reacting to. They're likely to be allergic to any other drugs which also contain sulfur, which will include the sulfonyl ureas, which we met earlier in the course, because these are hypoglycemic drugs, and also sulfasalazine, which we also met earlier very briefly in the course. This is a drug which is used to treat Crohn's disease. So if someone is allergic to sulfur, then you have to watch out that they don't get any of the drugs which contain sulfur, and that won't just be drugs in this class either. Also acting in this same way, but not via the folic acid synthesis, these ones go directly and meddle around with DNA synthesis, are the quinolones. And the ones that you're going to be seeing are the names ending in floxacin. These are actually fluoroquinolones. They're kind of later generations, and these are the ones that are going to be in use largely. So when you see floxacin, it's a quinolone. Broad spectrum again, relatively broad spectrum I should say, so there are some active against gram-negative bacteria and some gram-positive, but not all gram-positive. They are bactericidal. These ones again are being kept in reserve as far as possible, because if we've got drugs that certain nasty bacteria are susceptible to, we don't want to use them unless we actually have to, because we'll simply hasten the development of resistance against those drugs. And we really have to be much more cautious now about, if we have something that's still usable, not overusing it. They also have a potential to cause some dodgy effects. They can cause photosensitivity, meaning that if you take in these drugs, you have to be a bit careful to cover up from the sun, because you are likely to burn much more readily. The sun will have a much more effect on you, which is also true actually of the tetracyclines to a certain extent as well. They can cause dizziness. We don't normally associate that with antibacterials, but this is probably the one that's most problematic. It's this joint damage. They can tend to cause musculoskeletal problems and damage to joints, particularly in young developing joints. So they're only available for use in children in very, very specific circumstances, because there seem to be additional risks with the use of these drugs. Again, it always becomes a risk-benefit calculation that you have to make. If a child has a life-threatening infection against which the quinolones are going to be effective and there isn't much else available, then obviously you will use it. If there is something else available which doesn't have the potential to cause musculoskeletal problems, then you won't use the quinolone. So those calculations have to be made all the time now. Gone are the days when you could just pick up your tetracycline, your broad spectrum, and give it to everybody.